Ali, thank you very much for coming out here. Come on up and take the floor.
Thanks, Scott.
Great. You're all set?
All set? Yep.
Excellent.
Good. Hello, everybody. Thanks very much for coming today. I want to thank Tekka as well for having me today. Today, as Scott mentioned, we're going to discuss and focus on radiant floor heating design. We're going to review some of the advantages of radiant floor heating in general. So this is me. I'm a technical sales engineer with Reha for about 7 years now. I work out of sales office, Vancouver. A quick history of our company. Reha was founded back in 1948. It's still privately owned company, owned by Mr. Wagner out of a tiny little town called Reha in Germany, on East Germany back in the day. We have about 20,000 employees spread around the world in 54 different countries. Our head office for North and South American operation is located in Leesburg, Virginia. And in Reha, we basically have three major divisions: construction, automotive, and industry. Construction is basically my division, where we manufacture polymer products for radiant heating, snow melt, radiant cooling, district energy applications, geothermal applications, as well as manufacture UPVC window and door frames. Under the automotive, we manufacture a lot of gaskets, components for cars on the road. And under the industry, we manufacture lots of polymer stuff for furniture, for Boeing and Airbus airplanes, lots of plastic gaskets there, like tilt tables on the planes. They're more likely a Reha product. And the reason I discuss about this is that we manufacture our own resin, the base material of plastics. Unlike some other of our competition, sometimes they're running into issues with resin shortages. But as we consume, as you can see, consume a lot of resins, we have our in-house supplier for resins. So these are some of our products for Mercedes and BMW. That's what we manufacture for Audi model A3. We manufacture 50,000 different parts in that car. Also, there are over 200 different stadiums around the globe that they are tooled up with our turf conditioning system, where we install PEX-A pipe under the turf to basically condition the turf during the winter and summer. We have 4 sales offices in Canada, 5 in the US, and 3 in Central America. And we have 4 different training centers. One is in Canada, in Burlington, Ontario, and in Minneapolis, Leesburg, and in Pullman. And the Pullman, Alabama is our plant where we manufacture most of our products for North America. This building here is where we manufacture our PEX pipe, and that's this building here, and the rest of the facility, which is 800,000 square feet, where we manufacture our products for automotive division. So that was a rundown about our company. So we're back on our presentation. So today I'll talk to you briefly about the comfort limits set by ASHRAE Standard 55. We're going to quickly review that, and then we'll review the advantages of radiant floor heating. We'll review the design process and do a quick mock-up sample project together. And then in the end, we'll review some tips and points about the floor covering in radiant floor heating applications and the control options that we can have with a radiant floor heating system. According to ASHRAE Standard 55, thermal comfort is that condition of mind which expresses satisfaction with the thermal environment. So ASHRAE has done a lot of study throughout the years, and they come up with some boundaries. For operative temperatures during summertime, they say, okay, we need to stay between 71 to 80 degrees, and during winter time between 66 to 77, to be in that comfort zone. And the range of floor temperature, which is our focus because of the radiant floor heating or cooling applications, they set a guideline here that has to be between 66 as low limit and 85 as the high limit. That's for occupied areas. So when we are doing design for radiant cooling applications, that would be our limit right there, as well for radiant heating applications. So There are 7 primary benefits listed here for radiant heating application: adaptability, architectural freedom, comfort, control, efficiency, longevity, and safety. And we'll review these quickly here together. When we say adaptability, we mean that you can install that hex pipe in the floor, in the ceiling, or on the walls. So, and that pipe is also not exposed. It's embedded, it's an emitter that's embedded in the floor and the ceiling, so you don't really see it. And the radiant zones are easily zonable, and you can heat the entire building with the radiant floor heating. Or you can also mix it with other heating systems. And for the heat source, you can also couple the radiant floor heating to almost any heat source. Condensing boilers, geothermal applications. It brings us to the adaptability here. Integration with ground source heat pumps is very easy, and it's a good system if you use a ground source heat pump, because these systems work at very moderate and mild temperatures. The lower the temperature is, the higher coefficient of performance you'll get. So they will become even more efficient if you actually use a ground loop to run your radiant heating or cooling system. From architectural standpoint, if you use a radiant heating or cooling system, you'll have much more freedom. This picture shows, it's actually the O'Hare Airport in Chicago, and it shows the air convectors there. Cases, they're big, they're bulky, and they will take up some space. But whereas with radiant heat or radiant cooling applications, your pipe will be installed in the floor, in the ceilings, or behind the walls, and you have more freedom to move around your furniture or things like that. And here's a simple fact that this is an example that a 1-inch water pipe can carry the same thermal energy as a 10 by 18 inch rectangular duct. So you would require much smaller space to carry your heat source. From the comfort standpoint, this graph here on the left, it shows the optimal comfort profile. The middle one is the radiant floor heating, and the right one is the forced air. And if you compare them, you see that the radiant floor heating is very close to that optimal thermal comfort. And that's because you will have a little bit of natural convection that occurs if you have a heated floor. It comes up, and that's where you need it to feel comfortable. You will also, your foot is touching a warm floor, so it will bring you a little bit more comfortable environment compared to forced air, where we have stratification as well with the forced air application. Also, with radiant heating systems, you will have a cooler set point in your room, and we'll discuss further details about that. And with a cooler air, you have a higher relative humidity in the room. So there will be less dry skins and fewer dry throats. There is no ductwork necessary for radiant heating applications, so that will eliminate allergies and some dust. And also, as I said, all your surfaces are kind of warm, so you will be in a more comfortable environment in general. From controls standpoint, generally speaking, a given radiant heating circuit or loop can serve somewhere about 250 to 400 square feet of area. And when you connect that loop to a balancing manifold like this, you can easily control each given area. And when you hook it up to specially designed radiant floor heating thermostats, you also have the option to connect a floor sensor to it to prevent potential damages to hardwood flooring, for instance, which we again discuss further details. And you can also install these zone valves on the return side of your manifold and technically control every loop, every single loop. If you have a bigger open area like here, you can actually gang 3, 4, 5 of them together and then have them open and close all together. So your control options are better and easier with this system. From efficiency standpoint, as your indoor design set point is lower compared to a forced air application, your overall heat loss will basically reduce by 4 to 8% because your delta T between your indoor temperature and outside temperature is going to be less, so it's going to be less heat loss. And then on top of that, your infiltration heat loss will also be reduced. That's also going to be affected by the type of the building, how tight the building is, and the R value of your panels, the exterior panels. But the infiltration heat loss will also be reduced from anywhere between 5 to 40%. And overall, 10 to 25% reduction in your overall heat loss. And it's going to be more efficient by using the boiler, like condensing boilers or geothermal systems, because as I expressed earlier, it's going to be a mild temperature, usually somewhere around 110 to 120 degree. So it's a good combination with these high efficiency heat sources. And this is another example. A 3/4 inch water pipe can transfer the same energy as 14 inch by 8 inch duct, which means that you will only use a 60 watt circulator versus a 1500 watt fan. So there is another energy efficiency. From the longevity standpoint, as we're using a PEX pipe, the product that we manufacture is a PEX A pipe, so they're durable. 25 years is the very regular average life expectancy of that product. And also, as this pipe is going to be embedded in concrete floor or behind the walls, you don't really need to do any services. There's no filters, there's no air ducts, there's no maintenance involved for the radiant floor heating systems. And from the safety standpoint, as shown in this picture, some baseboard heaters they get really hot, whereas radiant heating systems are very moderate. The maximum temperature you will get for your surface temperatures would be around 85 degrees, so it's not going to be any hazard. Whereas with some other emitters, there's a safety issue there. So that explains the advantages of radiant floor heating in general. So now we're going to jump on the design process. We're going to review the heat loss process. It's going to be very generic. I'm going to touch on F280 as well. But this seminar is not the training on heat loss calculation. We're going to just touch on some basic formulas, and then we review the panel requirement, the BTU per square foot for a radiant heat system. And then based off that, we're going to calculate our required floor temperature to achieve that heat loss. And then we're going to determine or size our PEX pipe spacing, circuit lengths, and the required water temperature. And the step 3 is to calculate our flow rate going through the loops and our entire system. Then we can determine our head loss, and based off these two information, we can size our circulator, and in the end, how we can size our expansion tank, which is very important in our heating system. From thermodynamics, you know that there are three modes of heat transfer: conduction, which is direct contact. Then we have convection, which is a fluid transfer the energy. That fluid could be air or water. If the fluid is air, warm air is light, so it goes up. Cold air is heavier, so it comes down. So you have that effect of convection heat. And then obviously you have radiation. Warm objects radiate heat waves to cooler objects, similar to sun heating the earth. And there is no air in between, right? So that just heat waves. All of these modes of heat transfer require a delta T between the two objects. If you're required to have a delta T, let that heat transfer happen. Throughout this presentation, we're going to touch on 3 different types of delta T's. Delta T number 1 is the temperature difference between indoor and outdoor. Delta T number 2 is the temperature difference between your floor surface temperature and your ambient temperature. And delta T number 3 is the temperature difference between your supply and return on a radiant heating system. So these are the 3 delta T's that we're going to touch in here. When we want to do a heat loss calculation, we have to have information about our outdoor design temperature. And that information is available from different sources. One of them is ASHRAE, the other one is the Canadian Standard Association. And there are basically three approved methods that we use with our design software: ACCA Manual J, ASHRAE, and CSA F280, as Scott mentioned. And when you look at the ASHRAE charts, it's going to look like something similar to this. We got it from ASHRAE 2009 Fundamentals, Chapter 14. Let's take this example, Anchorage in Alaska. You have two outdoor design temperatures, minus 20.2 and minus 22.7, at 99% and 99.6. First of all, ASHRAE, for example, they gather that data. It's not simply the coldest temperature on the record. What they do, they basically refer to a time frame between 3 to 5 years and basically provide that information based on that time frame. And these percentages, for example, that 99.6 means that only 0.4% of the days throughout the year, which is going to be about 35 hours, is going to be colder than this temperature. Okay, based on the information that they collected for a 5-year time period. Usually, we use 99% or 99.6%, and that should suffice, because only 35 hours throughout the year, this temperature or your outdoor design temperature may go below that minus 22.7, which is fairly acceptable. Here again, we are not going to discuss any details about the different methods. It's just an overview of some maths that are generic calculations to do some heat loss calculations. So the first formula that we're going to touch on is to calculate the conductive heat through the exterior panels. And that formula is the area that you have, your delta T number 1, which is the temperature difference between your indoor design temperature and the outdoor design set points. And you divide that by the R value of the material that you have as a panel in between the two temperatures that you have. We usually get that R value from manufacturers or from ASHRAE tables. And one thing that you need to note is that you need to calculate the convective heat loss through every exterior panel and every panel with a temperature difference. For example, if you have a house and you have an attached garage to it, your set point for the house is 68 and your garage is going to have a set point of 60, you still have a heat transfer between the house and the garage. So you have to also calculate that. It's going to be a heat gain for the garage and a heat loss for the house. And that's important. And that's where we get our R values from ASHRAE tables listed on the materials, or there are some good information on some design softwares such as LoopCat. That's the design software that we use for our heat loss and radiant calculations. And for windows and doors, manufacturers provide a U value, which is the inverse of the R value. So in Reha UPVC windows, we have a U value of 0.35. So you divide that 1 divided by 0.35 to 2.85, which is the R value, for example, for a Reha UPVC window. As a side note, for radiant floor heating applications, we always account for a radiant back loss, and you will see that on our design submittals. I just had a discussion a couple of days ago with one of the engineering firms in town about the same topic. When you have a heated thermal mass, being a concrete or whatever the thermal mass is, you will have some directional losses going downwards to the floor or to the subfloor, to the soil, and also you have some escape of the heat through the edges of the slab. And we always account for that. When you have a forced air system, your floor is not that warm. So the amount of that heat loss through the floor is going to be much less. Whereas when you heat up your floor and create a thermal mass, that heat loss is going to be greater. And that amount is all dependent on the amount of R value that you have for your floor or edge insulation. So you have to be careful when you're doing your heat loss calculation there. So this is our sample project. This is the location of the project is in Anchorage in Alaska. It's a 40 by 40 building, 10 feet high ceilings. And our outside design temperature, we got it from that chart as I showed you, minus 23. And your indoor design set point, we set it to 68. Usually for hydronic applications, that temperature for indoor design set points, we usually set it between 68 to 70. For forced air, it goes up higher. But with radiant heat, if you really crank up the thermostat, you create a big thermal mass in there, and it takes a while for that temperature to go away, especially on shoulder seasons. So be careful about that. Indoor design set points, somewhere between 68 to 70. In some applications, we go up to 72 as well, but you don't really need that much because all your surfaces are warm, and that increase your mean radiant temperature, which is the average temperatures of all the surroundings. And all these surfaces will radiate heat to all other objects in the room. With the forced air system, this table is cold. It doesn't matter if it comes up the hot air, but with a radiant floor heating system, the radiation will even heat up the table, the walls, the ceiling, all the objects surrounding. So that will increase your mean radiant temperature, and you really do not require to have your set point set higher than 68 or 70. You don't really need to do that. Okay. So usually when we do heat loss, we do it room by room, based off the R value of each room. But for the sake of our conversation here, we're going to treat that as a big open area. So here we have this wall number 1 and number 2, they're more or less the same, and number 3 and 4 that has some windows and doors on it. We got the R values from the architect. They told us that yes, the walls have R20, ceiling R38, the insulated floor has R7, windows are R2.5, sorry, R7 is for the door, and R10 is the under slab insulation, which is equivalent to a 2-inch polyurethane insulation. So for wall number 1, we have the area 40 by 10, that's our area of our wall. Our delta T between our indoor design set point of 68 and outside design set point of minus 23 gives us 91 degree as our delta T number 1. We divide that by the R value for that wall, which is R20. So we have 1820 BTU per hour heat loss through that panel at wall number 1. It's the same thing for wall number 2, but wall number 3 has some windows and doors on it. So we deduct the area for the windows and doors. That will give us that area square footage available for the wall itself. So we calculate accordingly. For the window, we're going to plug all the area square footage of that window to the same formula with the relevant R value. And when we do that, you sum them up. So for wall number 1, 2, 3, 4, and for the ceiling, we did the same thing. And for the floor, we use another formula. This is not the formula that we use to calculate the heat loss through the floor. Because of the directional heat loss through the edges and through the floor, it's another same concept, but it's more complicated formula. We have to get the soil conditions, the moisture content of the soil, and some other parameters in there to calculate the heat loss through the floor. But we did that, so you sum them up. That would be your total conductive heat loss through that building. Now we need to calculate the infiltration heat loss. ACH, which is the air change per hour. It's a fraction of air volume changed in 1 hour. Usually for residential applications, that value is somewhere between 0.3 to 1, which means that if you're at 0.3, it means that 30% of the volume of the air in the dwelling will be changed in a 1 hour time frame. For some applications, commercial applications, if you have bigger apron doors, bigger doors, you have more air change, that value can go up equal to 1 or sometimes even more than 1. And obviously the air change rate is going to be affected by the building tightness. These values, we got it from ASHRAE. There are some definitions on ASHRAE. This is the average quality building, like a typical residential building that is built or constructed today, with average quality windows and doors. Major penetrations are caulked and things like that, but a good quality window or door, or if you apply spray foam, that will bring us to that tight construction category. In some cases, we design radiant floor heating for a retrofit application, which is an older building. When we use our panel systems like grout panel or grout plate, those are older buildings, so we need to account for that building tightness when we're doing our infiltration costs. And this is the basic formula to calculate your air infiltration. This is a constant value, 0.018 BTU per cubic feet, degree Fahrenheit. You multiply that by your volume, and then your air change per hour, and then you multiply that by your delta T number 1, which is again temperature difference between your indoor and outdoor temperature. And for our example, we have 40 by 40 by 10, so a total of 16,000 cubic feet for our volume. For this particular application, because it was a commercial building with big doors, we decided to go with air change rate of 75%. And then same 91 degree as our delta T. Plug in those numbers, that will give us 19,650 BTU per hour as our infiltration heat loss. And then you add the two together, that will bring you to the total heat loss of 37,275 BTU per hour. We round it up to 38,000. One thing that is important, that this number has to be the output of your heat source. So if you're using a boiler that's 90% efficient, that nominal size of that boiler has to be 10% more than that. Alright, for radiant floor heat applications, sometimes we don't have all the floor available to put our pipe in. Sometimes you have kitchen aisle, the cabinet islands. Sometimes you have the fridge sitting there. Obviously, we don't want to put any pipe under the fridge. So usually the rule of thumb is that we usually go with 90 to 95% of the area square footage of the total house as our available area to install our pipe. If you're short in terms of heat output, you always can install the pipe in the wall, or sometimes in the ceilings for areas that we don't have enough floor area available. So again, back to our example, you're not going to put any pipe in 150 square feet because there's a big counter right there, and the owner doesn't want us to put any piping in there. So the available area that we have is 1,450 square feet. So we divide our total heat loss by that value, which will bring us to 25.7 BTU per hour per square feet. Again, we round it up to 26. So our panel, our heating system, radiant floor heating system, has to bring us 26 BTU per square feet in order to meet that heat loss. Okay, so we sized our panel there. And now we need to configure what the floor temperature should be. That HTC, it stands for heat transfer coefficient. It's not the other HTC. So heat transfer coefficient, the required output, you divide that by the HTC, which is usually 2 for a radiant floor heating. Give me 1 second, I'm going to discuss further about that HTC on the next slide. And then you add your target indoor air temperature to that value. That will give you the required floor surface temperature. So in our case, again, 26 divided by 2, that's our delta T number 2, by the way, and you add your indoor design set point of 68. So your floor temperature has to be 81 degrees in order to provide 26 BTU per square foot. Okay? When obviously the outside design temperature is minus 20. Okay? That HTC, which is the heat transfer coefficient, it's true for a radiant floor heating system due to the natural convection. And it comes down if you have pipe in the walls. That's 1.4. And it's even less when you install your pipe in the ceiling, because you will lose that natural convection effect of the heat. It's the other way around when you're doing radiant cooling design. These two numbers will be reversed. So for radiant cooling, your floor capacity is less and your ceiling capacity is more. So when we're designing radiant cooling systems, we usually go with concrete core tempering, so we don't put any insulation. So that floor there act as a radiant floor heating and cooling for the floor above, and it will act as a radiant ceiling heating and cooling for this floor here. And it's known as concrete core tempering. Very effective, very efficient. Obviously you need to have forced air system for sure, because that will take care of your latent heat. The radiant cooling will only take care of the sensible heat. But the forced air system will control the relative humidity and the latent heat portion of it. But it will be certainly downsized dramatically if you go with concrete core tempering. Anyways, for some applications, if your indoor design temperature is less than 68, for example for a big warehouse, then your HTC can even go higher because you have more convective effect. And in some cases, such as greenhouses, whereas your indoor design set point is close to 80 degrees, your HTC will come down a little bit further. So these things has to be considered when you're doing your heat loss calculation and the panel output calculation. So in a radiant floor heating application, in general, we have these 4 major or 5 major floor sections. Perimeter area, which is about 3 feet away from the outside walls and windows. Occupied areas, that's whatever that's within. And then we have areas with bathroom. Distribution hallways, where you have your manifold installed and all your piping is going to be distributed from that point on. And areas that you're not allowed to put any pipe. Scott mentioned about some guidelines in TECA, which is very good and very handy. For example, for perimeter areas, we have to follow TECA guidelines, and in there they say you have to stay at 6 inch on centers for perimeter areas. Why? Because that's where you have your most heat loss. And those areas that we have to have a tighter pipe spacing, your floor temperature can also go up to 95 degrees. You remember, based on ASHRAE standard, our floor temperature limit is 85. If it's more than 85, you don't feel comfortable. It's too warm, too hot for your foot to touch it. But in some cases, if it's a warehouse and everybody's going to walk with their shoes on, we can increase the temperature. We can crank it up high to 90, 91. So it depends on the application. But as a general guideline, occupied areas, your maximum floor temperature is 85 degrees, which will bring us to maximum 34 BTU per square foot output. Where did I get that? From the previous formula. If you plugged in these numbers into that formula, that will give you the maximum 34 BTU per square foot output. For perimeter areas where we have our tighter pipe spacing at 6 inch on centers, we can go up to 95 degrees according to ASHRAE standard. Because those areas, not so many people are going to walk there and stand there for a long period of time. So we can have more heat output for our perimeter areas. For bathrooms, again, the level of comfort, that study shows that if it's up to 91 degrees, it's even better because people feel more comfortable in a bathroom with a floor temperature of 91 degrees. So we can increase that to 91. And for distribution hallways, where you have your manifold and you have no other choice but to run all the pipes, supply return lines, you can go up to 95 degrees as well. Not for the entire floor, but just for that section. In some cases, that there are too many pipes going through a very tight spot, sometimes we insulate the supply line, every other supply line basically, to reduce that hot spot effect if it happens. But we are allowed to go up to 95 degrees. So now that we have calculated our heat loss and the output panel and our floor temperature, now we need to size our pipe. These are some questions that you have to ask. How will the pipe be installed? Is that going to be installed in a concrete overpour? What is the thickness of that concrete overpour? The reason you have to ask that question is all the radiant heating, or basically, PEX manufacturers or radiant designers, they require a minimum of 3/4 inch coverage of concrete from the surface of the pipe to the surface of the floor. And the reason we require that is to prevent any cracks or any damages to that concrete overpour. So we need to have a minimum of 3/4 inch coverage. So if your overpour thickness is only limited to 1.5 inches, your maximum pipe size can only go up to 5/8 of an inch. You can't install 3/4 of an inch because your OD of that pipe is bigger, and you will have less coverage from on top of your pipe. So that's something that you have to consider. Of course, in some cases, it's a retrofit application. It's an older house. You can't really do any overpour. The building is not capable to handle the load of concrete. So in such cases, there are some options like this, which is ROW panel system. These are just aluminum panels that you install on top of your subfloor and then install your floor covering on top of it. So if that is the application, your pipe size will be 3/8 of an inch. So as you can see, the application and the type of installation will dictate, in some cases, will dictate your pipe size. That's something that I want to mention. And then obviously the floor covering is very important. These charts give some ideas about the R value of the floor covering, and it can be as low as 0.2 for vinyl, and it goes up to 2.1 for a thick carpet. This will certainly affect your pipe spacing and your flow rates. And we always recommend to avoid thick carpet because it will trap the heat in there, and it has some side effects for the performance of the system, which I'll discuss on the next few slides. So the available pipe sizes, most manufacturers offer these sizes from 10 millimeter goes up to 1 inch for typical radiant floor heating system. For pipe spacing, the tighter spacing that you have, it will reduce the water temperature, it will reduce the stripping, the cold spots, and you have a better response time in your system, and your general efficiency of the system will be better. Yes, you're putting more pipe into the floor, but your efficiency and your operating cost of your energy consumption will be much less down the road. Then you need to consider your maximum circuit lengths, which again, all of this are on TECA guidelines, and that means how far your fluid can go before it's too cold and it doesn't perform well. And then the final step would be calculating the required water temperature. And usually designers use particular software to calculate that number. Some considerations, again, to size your pipe. For example, if you go with a smaller pipe, it's more flexible, easier to install, and it's less money, obviously. But your loop lengths cannot be as long as a bigger pipe. So if you have if you have a big open area that from here to the end of that room is, let's say it's 200 feet long, you can't run a 1/2 inch pipe because you need a very huge pump to pump that fluid through it. If you want to go 200, then come back 200 plus your tails back to your manifold, you're sitting at 450 for one loop. That's a lot of length for a 1/2 inch pipe. In that case, you would require to get a bigger pump. So that's not a cost saving there. Plus you're losing your efficiency there. So it's always a give and take. You have to consider all these things when you're try to size your pipe, you need to consider the pump sizing as well. This chart gives you some typical pipe spacings that are available. Again, for a residential application, slab on grade. For perimeter, it's 6 to 8 inch. Some jurisdictions, there are some guidelines, such as in BC, we are following TECA guidelines. So when I stamp my design with a TECA stamp, I have to stay with 6 inch on perimeters because that is what the guideline is asking for. But for occupied areas, that pipe spacing can go from 8 to 12 inch on centers. Don't go beyond 12 because that will cause stripping and cold spots in the floor. Unless it's a commercial applications that you can go up to 18 inch. That's typical when we design for warehouses and applications like that. But for residential, don't go beyond 12 for your pipe spacing. And these are some other numbers. You have a printed copy, by the way, of this presentation. So if I'm a little bit want to rush it through some of the slides, you always can refer back to that or give us a call and we can certainly have a detailed discussion if you have any questions about any of these. Now, if you remember, we discussed the delta T number 3, which was the temperature difference between our supply and return on our manifold for the radiant heating system. That value, we usually go with 20 degree, which is a typical industry standard. In some cases, that delta T was lower than 20, which is basically result in a better, faster response system. But if you lower your delta T, that means that the fluid has to travel quicker to come back, which means that you have a higher velocity, a higher flow rate, higher head loss, bigger pump. So you always have to consider that again. But that 20 degree is nominal, it's very typical, and you can always refer to that. Large diameter pipes hold more water. Obviously, more BTU can be pumped with a larger diameter pipe. So with a larger diameter pipe, you can have longer loops because you're carrying more BTU and it takes a little bit more distance to lose that 20 degree. So that's why you can, with large diameter pipe, you can run longer loops. Okay. This chart here shows the typical maximum circuit lengths for a given pipe size. For example, for 3/8 pipe, the maximum loop length you can run is 250 feet or 76 meters. For 3/4 inch is maximum 500 feet or 152 meters. And these are not absolute maximum circuit lengths. I was designing a snowmelt system in Mica Creek for a BC Hydro application, and the loads were insanely high in that area, and I was using a 3/4 inch pipe. I couldn't run them nearly 500 feet. I should stop somewhere around 350. Otherwise my pumping would jump up the roof because my snowmelt load was so high and I had to run a higher flow through my pipe, so that resulted in a higher head loss. And we had a discussion with the engineer back and forth to settle it down. So I had to design that system with 3/4 inch pipe. Maximum loop length was 350. So there is no absolute maximum. It all depends on the application. In some cases, you can actually run longer loops. So now we want to calculate the water fluid. We actually use a formula. We're not going to discuss details here, but that temperature has to have enough BTU, so you can basically pump enough BTU to go through that thermal slab and then through the floor covering and into the space. We always have to account for that radiant back loss. If you see anywhere between 5% to 20% as a radiant back loss on our design submittals, that's the reason why. In cases, if you account for a safety factor on your heat loss calculation of whatever percentage, that will cover that. So we don't want to overkill. We don't want you guys as engineers to account for a 10 or 15% safety factor and then we add another 20% for the radiant. That's an overkill. So we have to have an open line of communication in that case. closest to reality as possible. So the radiant fluid temperature is based on all these parameters: heat loss, pipe diameter and spacing, circuit lengths, conductivity of thermal mass, which could be a concrete floor or a radiant panel, and the R value of insulation that you have under your panel and on top of your panel, which is the R value of the floor covering. And then we plug in all these parameters into a formula to calculate the supply water temperature. We usually do that through our design software, LoopCAD. Cool. 140 degree is the maximum supply temperature when you install your pipe in a concrete floor, unless otherwise approved by structural engineer. It's not a temperature limit for the material like the pipe. With most PEX pipes, you can run 180 degree at 80 psi, so that's no problem there. But if you're installing that pipe in a concrete floor, 140 degree is your maximum supply temperature, unless otherwise approved by the engineer. So back to our example, we calculated a total 6 circuits to cover the entire area for the warehouse, office, and bathroom. The owner wants us to have 3 zones for these 3 areas. In some cases, you are able to have all your loops at the same length and keep them within 5%, which is nice. But in some cases, it's really hard to do due to the shape of the rooms and even due to the different heat loss for each given room. Maybe you have 2 similar rooms, but they have 2 different heat losses, and I think I have. Yeah, I think I have a slide there, and I'll explain that to you. But not all the loops are the same length all the time, because of different shapes, because of different applications, and in such cases, you have to use a balancing manifold, so you can control the amount of BTU you're pumping to a given area. So this is the hydronic flow rate formula, one of the most famous formulas I've seen. In order to calculate your required flow rate, you need to divide your total BTU requirement by the fluid density and specific heat. You multiply that by a delta T, which is the maximum temperature drop between your supply and return line. That's our delta T number 3. And then multiply that by 60. For water, our fluid density and specific heat are these 2 figures here. And when you plug in all these here on the next slide, with a 20 degree delta T, this value here can be 10,000. So if you're dealing with a radiant heating system that's going to use exclusively water, if you divide your total BTU by 10,000, that will give you the required flow rate. But bear in mind, that's just based off water. If you're mixing any glycol mixture for freeze protection, that will change that value there. And another note, all the head loss tables that are used here are based on US gallons, not imperial gallons. So we can keep that in mind if you're doing your calculations based off imperial gallons. So back to our example, our total heat loss was 37,275 BTU. We divide that by 10,000, so 3.7 would be our total GPM for the entire system to deliver 26 BTU per square feet to meet that total heat loss. All right? If all of our circuits are the same length and the same heat loss, we can divide that 3.7 by 6 and get the GPM per loop. But that is not the case, because in some applications, for example here, this is just an example, we have 2 similar rooms, same area square footage, but this room has 2 exterior walls and a couple of exterior windows. This room, same area, but 1 exterior wall, 1 exterior window. When we did our room by room heat loss calculation, we came up with 10,000 BTU per hour for room A and half of that for room B. Which means if we divide 10,000 by 10,000, we require 1 GPM for room A and we require half a GPM for room B. So in this case, we are using the same amount of pipe, but the flow rate has to be different, 1 and 0.5. In this case, using a balancing manifold is always helpful. With these balancing manifolds, you have a balancing valve on the return side underneath that blue cap. You also have a flow gauge on top, so when you adjust your flow on your balancing valve, you can see that on the flow gauge. And by doing that, you can accurately pump enough BTU to a given area for a required heat output. As a side note, quickly touch on the antifreeze. In some cases, you need to protect your fluid from freezing. So based on your freeze protection temperature, you can see what is the volume percentage that you would need to put and mix your system with. If you do that, you need to redo your calculations. That 10,000 number that I showed you on the previous formula, that will change because the specific heat and the density of that fluid will also be changed. And when you're adding antifreeze, that will certainly affect your output because the specific heat of all the antifreezes are worse than water. So in cases that you need to add antifreeze, you probably end up having a higher GPM because of the specific heat, and also because those fluids are more has a higher viscosity, higher density. Again, if we go with 50% antifreeze for our example, when you plug in all those numbers into that formula, you see the required GPM will be 4.2, whereas we calculated 3.7 for water, just straight water. All right. So we determined the heat loss, we choose our pipe size, the flow rate. Now we want to calculate our head loss going through each loop. Before we do that, we measured the required GPM for every individual loop, and we had a total of 6 loops. One of them has a higher GPM because it's a longer loop and it's serving an area with higher heat loss. So that 3.7 is going to be divided just like this among these 6 circuits. Now we can refer to the head loss tables. Reha has head loss tables. All pipe manufacturers, we all have a head loss chart. You can refer to that. And some of them it's based on PSI, some of them based on feet of head. So be careful about that conversion. You always can use design softwares too. It's an easier way of calculating your head loss. The LoopCAD is the software that we use, and Reha offers a free version of LoopCAD. It's a non-graphical version. You can do a quick heat loss based on F280 spreadsheet, and also you can actually use that as a calculator for your head loss calculator. So all you need to do is choose your pipe size, that's 1/2 inch, your flow rate going through that, your length of your circuit, and the type of fluid, which is in this case 100% water, and that will give you the total of 3 feet of head. So we did that calculation. Circuit number 1 through 3 is only 3 feet of head. 4, 5 feet. Circuit number 5 is 7 feet of head, and circuit number 6 is 5 feet of head. Should we add them all up, or should we go with the maximum? That's the one. We have to go with the maximum head loss through our loops because they are actually connected in a parallel pattern. If they were connected in series, then we had to add them up. That's what we do for the flow rates. But for the head loss, we always go with the maximum. In this case, it's 7 feet of head. So our radiant loops has the maximum 7 feet of head. Then we refer to the charts for the manifolds. In this case, we have total of 3.7 GPM for a 6-loop manifold. That's your 6th line right here. So where they cross each other, you come back here and that would give us 0.6 feet of head through our manifold itself. So you can use these charts, or again, you can refer to the design software. Again, in LoopCAD, you can choose your size of your Pro Balance manifold, which is 1 inch in our case. Flow rate 0.7. Total number of loops is 6. Oh, no, 3.7. Sorry, 3.7 is our total GPM. 6 loops, and then it will give you the feet of head, which is 0.6 in that case. This is a conceptual piping. There are so many items missing in here, but just for the sake of our conversation, if we have a heat source, we supply our hot water through a circulator to our manifold, 10 feet of 3/4 inch pegs, and then 10 feet back. We calculated, or we got the heat source head loss from their literatures. That's 3 feet of head. From the head loss charts, or from the LoopCAD software, we plugged in 10 feet of 3/4 inch pipe as 0.75 feet of head as its head loss. The manifold will calculate 0.6. Our circuits has 7 feet of head. That was the maximum that we choose. And then the return piping is also has 0.75 feet of head. So we add them all up. 12 feet of head is our total head loss for our piping, for our simple project. In case, if you have heat source in your basement and you have your manifold on the next floor above, you have a 10 feet elevation. Do we really care about that? No, because we are just circulating water through the system. It's a closed loop. We are not pumping it. That's why we emphasize that this is a circulator, it's not a pump, because we are just circulating the water through a closed loop. If it was an open loop and if you're pumping the water out, then we should account for that elevation, but not in this case, because you go up here and then come back down. It's like a wheel. But in this case, we have 20 feet lines, so that will increase our head loss to 13.6 feet of head. All right. Now we want to select our circulator. We usually refer to pump curves provided by manufacturers. In most cases, a variable speed pump with an ECM module would be the best choice to adapt to various different flow rates. In our case, when you look at these curves, the pump performance curves, this is the area that you want to be. To the left of that curve, we don't want to be here because that shows that our pump is too small, and you don't want to be here because that shows that your pump is too big. Okay? So when you refer to this, 3.7 was our GPM, total GPM at 12 feet of head. So here, this particular pump here on this example is too big for us. So we went to another model, Grundfos 1558, very popular in gradient for heating applications. It's a 3-speed pump. So again, at the flow rate of 3.7, 12 feet of head, that's here, so we're good. At the medium speed, that's the pump that we need. So by doing this, you can actually size your required pump. Always try to avoid oversizing your pump. If you want to oversize, don't go more than 10%, because oversizing it will cause noises, excessive velocity and noise, and it cause corrosion in a copper pipe. So try to avoid oversizing. Like this 2699 Grundfos 3.7, 12 feet of head, it's here, it's too big for our application. You don't want to do that. And the last step is to size your expansion tank. And with the sizing expansion tanks, you require to measure the total gallons that you have in your system. This is a formula to calculate. You don't need to do that, but that's the formula. You have it in the booklet. On our product shop drawings, there's always a given value. It's a gallon per foot or liter per meter value there. So whatever is your linear footage length for a given pipe, you can calculate the required gallons. When you have that value, and if you're going to use a antifreeze, you can use the same number of gallons. If you want to go with 30% or 50%, that will give you the total glycol mixture or glycol volume that would be required, the antifreeze volume. So in this case, our half-inch pipe has almost 1 gallons per 100 feet. These are the other values for different pipe sizes. It's in the booklet for you to review. And so for our total 1,665 feet of half-inch pipe that we used for this example, we multiply that 1 gallon per 100 feet. That will give us 16.6 gallons for our radiant piping. And then you have another probably 15 to 16 to 20 gallons for your distribution piping that you easily can calculate that based on the size of your distribution piping. You need to also add the amount of volume that goes into the heat source, which is your boiler or could be your geothermal heat pump, and you add them all up for your total gallons required, and then you can refer to the charts from expansion tank companies, and then you can size your expansion tanks. But it's very important to have an expansion tank in a radiant flow heating system. Otherwise, you will see some pressure issues in the system. So, we did all that. We reviewed the heat loss for the space. We sized the radiant panel, the BTU per square foot requirement. Based on that, we calculated the floor temperature, floor surface temperature, and then depending on the application, we have been able to size our PEX pipe, the spacing, and the circuit lengths, and the required water temperature. We calculated the flow rates and the relevant head loss, and based on information from step 3 and 4, we have been able to size our circulator as well as our expansion tank. So, a couple of notes about the floor covering. One thing is about the carpet. As you see, the carpet has a high R value. When you want to use carpet, always try to use the thinnest carpet available in the market. And the best pad is a synthetic rubber pad, and a flat one, obviously, to reduce the R value of your floor covering. If you have a thick carpet with high R value, that will trap the heat in the floor. And you can't get the heat out unless you crank up your supply temperature, which defeats the whole purpose of having an efficient system. Also, that will also prematurely damage the carpet. So your carpet would also get damaged. So you don't want to do that. There is another tip about the hardwood floor, especially engineered hardwood floor. A poor design radiant heating system can damage a hardwood flooring. And the reason is, in some cases, you're pumping too much BTU. You're increasing your surface temperature. Most of the floor heating manufacturers are okay with 85 degrees, which is in line with the ASHRAE standard. But some of them, they don't even want to see 85. They tell you that it has to be somewhere around 80. There is no problem. There is no limit there. When we are doing the design, when we did that calculation there, as you could see, you can actually limit your floor surface temperature. In our example, we calculated 81 to achieve 26 BTU per square feet. But if there is any limitations from a flooring manufacturer, we can actually decrease that floor temperature and go backwards and see how much BTU you can get out of that floor. So it's doable that you limit your floor surface temperature during the design stage, as well as by using controls. If you have a floor sensor, you can install it, and that will override the reading of a thermostat reading on the wall. So these are the things that you also consider during controls strategy. And I encourage you to read this in your booklets. It's important. How to install a hardwood flooring. One important note that I need to mention is that when you're doing a nailed down engineered floor with sleepers, when the concrete guy come in and finish their job, you have to wait at least 28 days for that concrete overpour to cure. Otherwise, the moisture content in the concrete floor, if you install the hardwood directly on top of it after 2 weeks, all that moisture content will be absorbed by the hardwood floor and it will damage it. It's not a matter of radiant heating system. If you wait for that concrete overpour to cure for 28 days minimum, then you install your hardwood, it should work perfectly fine. And if you design it properly and use floor sensors when you have a hardwood system. So that was that. And then when you want to use or choose your control system, you always have to ask these questions. That first of all, if there's any controls contractor, you want to know where they stop their work, where you want to stop your work and where they're going to take over for the controls. In that case, you sometimes need to know whether the boiler system, how the boiler system is going to run. So you need to know what type of sequence of operation is going to be followed. Otherwise, your radiant heating system may not work the way it's supposed to. Also, you want to know who will occupy the building. What is the application there? Is there going to be an exercise room with quick changes? In that case, you need to design your system with a fast response system. Also, what temperatures are needed from the heat source? If your heat source, or basically this will affect whether you would need to have a mixing strategy. If you have a bigger heat source that's going to supply not only the radiant heating system but also a snow melt outside, you do not want to supply the same amount of energy to your in-floor heating system because that's an overkill. It's too much heat. You need to mix it down somehow or use a heat exchange strategy. And in the end, what is your smallest load in your system? And there is no definite answer for controls. It all depends. For example, a homeowner wants to have a remote control on their vacation. In that case, you need to design your system differently on the control side. In Rayhaw, we offer some sophisticated control systems known as Rayhaw Smart Control that you can connect with your phone, and there is absolutely no limits to how to control your system. But that is not applicable to every single dwelling because you probably don't need that much of controls over all components in your system. But in some cases, you may do. So for controls, there are some mixing strategies that you need to be careful about, and all these questions need to get answered. Always make sure that you use floor sensors if you have certain floor coverings. I need to wrap this up. Can't really focus more on the control side. I want to appreciate everybody here in the room. If you have any questions, let me know. We can have further discussion after this. There are also some tools that I bring here for you guys to have a look at, and these tools are recently launched by Rayhaw. They're known as Everlock Plus. We use them for radiant heating applications, snow melt, as well as plumbing systems. They're polymer and lead-free brass cold expansion fittings that are can be used with a PEX A pipe. If you have any questions or want to have a look at these tools, let me know, and feel free to ask any questions if you have any.
What's the advantage of using the PEX crimp fitting versus your expansion fittings?
The major difference is the ID of the two. So the expansion fittings in general have a bigger ID. So you will lose only about 5% of your inside diameter. Whereas a crimp fitting, it's an insert fitting, so you will lose a lot more. So that will certainly affect your pumping requirement and your head loss. So that's one major thing. And the second thing is if you're referring to a heating system, for example, Rayhaw does not recommend using a crimp system in a heating application because that ring may become loose due to expansion and contraction and temperature differences in the system. So we always recommend to go with a more solid connection rather than a crimp, just to be on the safe side. So these are the two major differences.
90% of the jobs are the crimp.
Yes.
No trouble.
Yeah. Well, we have seen trouble.
Both.
Yeah. And there is another thing that in some cases, if you forget to crimp your fitting, it will leak, and that's common. Again, I have seen it in a number of applications that there was leaks, and it was big, massive leaks. But with this system, there's no way that you can do it wrong. I mean, we try to minimize the defective installation. So that's another advantage. But the most important thing is the bigger ID that we have. Plus, with crimp fittings, you need to calibrate your tool probably every year or sometime sooner. But these tools, they don't require any calibration.
Something about 25-year life on the pipe, which is, or you can't be serious, it's only going to last 25 years.
No, it does.
Well, it's got to last 100 years. Like, what is the projected life of this stuff? Because if it's in an apartment block, since I mean, it's the end of the building, this stuff goes changing a boiler after 25 years is one thing, but blowing all the floors out of the building is something else.
Right. Well, that is not the life expectancy of the system. 25 years is the warranty that companies like us will provide. We still have the PEX pipe that is under pressure in our headquarters in Reha in Germany since 1970.
Have you seen
So, how many years that is?
Have you seen any failures from time for any reason whatsoever?
Well, if the pressure and temperature, the operating pressure and temperature of a given system is within the range, that's going to last even more than 25 years.
I would think, like my house, like I've been married for 25 years and it's gone instant, right? And, you know, like these, you're talking a serious problem in the building in 25 years is a lot. I mean, that's the end of the building. I mean, that's a major problem.
Yeah.
And just talk to the copper people about that.
Oh, yeah, I know, it's brutal. I mean, they gotta think about what they're doing nowadays, because that's a problem.
Yeah. No, it's proven. If the pipe is under the allowable pressure and temperature rating, it will last. At least we have proof that it's last for since 1970, and it's still under pressure and temperature test.
Do you have lifespan curves on temperature and pressure so that I could extrapolate if they were willing to
Yes.
go to lower temperatures or lower pressures?
Absolutely, absolutely. And in those cases, well, if you want to actually go beyond the expected pressure temperature rating, for example, if you want to run hotter temperature through the pipe, in some applications, recently I've been working on an application, we allow 200 degree through our pipe for a continuous operation. In some cases, 230 for a short-term exposure. But if if the application wants to circulate that water for a longer period of time at a higher temperature, we always can look at the extrapolation.
Well, the question was actually, could we extend the life by using lower temperatures and pressures? It wasn't how far you could push the product, but a 25-year lifespan would freak me out.
That is not the lifespan. Again, I have to emphasize on that. That's the warranty period. Like for a car that you drive, you get 3 years warranty bumper to bumper. Does that mean that after 3 years that car is a garbage? No. You still can drive it. You still can drive it,
Yeah,
but
you could probably compare it. So your open wars, your I think open wars is 30 years.
no, it's 25 for warranty purposes.
Right.
Yeah.
Right. So warranty is again, they're not saying lifespan, but can't help but compare that to copper. I mean, how many of the high rises are being re-piped right now from domestic, referring to domestic, after 10 years? So what's copper pipes warranty, by the way?
60 feet or 60 seconds.
Yeah.
Taillight warranty.
So what's your other choices, really? There's not a lot.
Yeah.
There's system choices too, right? You know, like, this is the delivery, so like the radiant system, like you have convectors, you have fan coils, you have lots of ways to deliver heat. This is a method of delivering heat.
Absolutely.
You know,
And those ones, what is the life expectancy of a fan coil, for instance?
But how hard is it to change a fan coil, and how hard is it to take a slab out?
Well, there is no need, honestly.
Take a slab out.
No, because when it's installed, and you have 25 years warranty, but that doesn't mean that after 25 years you have to do a slab and put a new pipe. No.
One of the advantages to this type of system is you got it in the floor, it's there for 80 years. It's probably the life of the system is for 80 years. So you pay more money for it, but that product has got a huge lifespan compared to just what anything else we put in. So that's kind of the question you look at when you're putting the system in. Is once it's in there, it's going to last forever. You change your board, you change your, with your heating system, especially with some of this high efficiency stuff, probably 12 years when you change a lot of these boilers because it costs to fix it. But that in-floor heating is going to stay there, as far as I'm concerned, like it's going to be there 80 years. It's like the poly D piping. It's a problem with the water systems and houses and stuff. But you know what? I get about 2 leaks a year with poly D piping in the floor in the house. Has been there for 30 years. And out of those 2 leaks I get, it's usually somebody putting your nails through something. And I don't think yours is warranted if you hit it with a nail.
Yeah, you can repair it and then put the fitting back into the concrete. You can install it back.
Okay, but your piping, I'm saying is your piping is not nail proof. Okay? So,
Yeah.
but that's the beauty of the stuff is it just lasts forever.
I actually get that a lot as well, as questions. Well, I'm a little worried about putting that plate there in the concrete, and then what if it fails? But nobody brings up the fact that you've got your walls are absolutely full of all kinds of plumbing pipe, water pipe and otherwise gas pipe.
Mhm.
And probably the pipe that's buried in the concrete is the most protected of all the pipe. That's probably the most reliable stuff, is that stuff you have protected in concrete. And
Yeah.
it's not doing the same thing.
Absolutely. And bear in mind, nothing is going to last forever. But when you do comparison between the other type of heat emitters available to us now, radiant floor heat will have a longer life expectancy compared to the other available options in the market.
Julia, question, comment, Gary?
Quick question.
Yeah.
You mentioned something about the floor sensors. Is something that can be used in case the flow rates or the whatever how it was designed is overly done.
Yeah.
And it will override the thermostat.
Right.
What type of floor finishes is recommended for that floor sensor to be accurate, so to speak?
Well, you can actually install a floor sensor even to control your low limits.
Right.
For example, for a bathroom that you have an in-floor heating system there, you can install a floor sensor for a bathroom with tile and then set a lower limit on your thermostat so that floor doesn't go below a certain temperature,
Yeah.
just for the sake of comfort. So it's not just to protect the hardwood flooring. It's to have an additional controllability of your system. But back to your question, those floor sensors can really control the surface of your subfloor or your thermal mass, mainly to protect the type of like hardwood floor covering that you have over top.
So it's embedded on the subfloor, not on the actual.
No, it's embedded if you have, it depends on the application. If you have, like, let's say if you have a concrete overpour,
Yeah.
you install that within the concrete slab. We usually use a piece of PEX pipe as a conduit
Yeah.
and then run it through that. The best place to place it is between two pipes,
Mhm.
not where you have your hottest supply line and not where you have your coldest return line. Somewhere in the middle and between the two pipe, and then you connect it to a special radiant floor heating thermostat that has the capability to connect the floor sensors to it, and you can basically set it up for a maximum floor and a lower limit, a maximum limit and a minimum limit.
Callie, if the floor sensor is in the overpour slab, potentially in the middle of it, let's say, and really what we're concerned about is floor surface temperature. How accurate is that relationship with the location of the sensor in the slab and with the actual, say for example, hardwood?
That's a very valid point, and that's where you, when you want to set it up on your thermostat setting, you can actually use some setting feature in there to calibrate your reading.
Okay.
That's the best way to do it by using some
Measure the
therm.
floor floor surface temperature and offset your thermistor.
Offset your exactly. Exactly. That's the best way of doing that, and that's the reason we have that option on the settings. And the best way to do that is to use these infrared thermometers. Yeah. But that's a very good point.
Any other questions?
Any other questions?
How's a huge amount of learning there? We have
okay.
a 1 week course, not 1 hour course.
Yeah, thank you very much.
Any
Appreciate
other
it.
questions for Thank you, Hallie. Very
Yeah,
much.
thank you very much. Thank you.